All right, welcome back. So today we'll be talking about standing waves, and then specifically we'll talk about standing waves in streams and standing waves in air column. And then we will also talk about beats between two um, waves or sound waves in that case. Okay, so let's take a look on standing waves. In strings first. So if you play any string instrument, okay, so like guitar or piano, so then the sound come out of the instrument. It's based on the standing waves you actually create in the strings. Okay, so um, so these waves are fixed in location. They are, but they oscillate with time. So if you have a string, you plug it and it will vibrate up and down. So it creates a wave, but it's trapped in this string. So so it will vibrate up and down. So then if we have, you can imagine this will be then just half of the wave, the one wavelength, right? Because the wave will be something like this. And then for this one loop will be just half of this guy oscillating up and down in that case. So this total length then will be just equal to half of the lambda of the wave you created, okay? Now, you can also create different waves in the same stream. So for this guy, so this then is um, the total length of the string then is equal to half of lambda. So then you actually have the longest wavelength possible because the wavelength will be equal to 2 times of L. And because the two ends are fixed, so that's because the two ends are fixed. So the two ends are not vibrating. So they are called antinodes, or they are called nodes. And in the middle here, it's vibrating the most. It's called node. Okay, it's called a node here. Now you can also create a different wave in this same stream here. Now you'll have a wave like this created, vibrating up and down. So there are three locations in the string, the two sides, two ends of the string, and then the middle point of the string actually does not vibrate. Okay, so those are the three nodes here, and then there are two locations that are called antinodes. They vibrate the most. Okay, so this is a second type of string of the wave you can create here. And in this case, you can see the whole, this is a one full wavelength of the wave. Okay, so then the length of the string is equal to lambda. So this is 2 lambda, this is then lambda. So you can see the wavelength decreases. And then the third one you can create is, again, the two ends are fixed, so they are nodes. And then you can add one more nodes in between, in the middle here. So there will be 4 nodes, 3 antinodes. Now you can see the whole string's length is 3 halves of wavelength because this is a full wavelength, this is a half wavelength. Okay, so 3 halves of that. So that gives you the wavelength for this third wave will be 2/3 of the length of the string. Okay, so wavelength goes down, but that means the frequency of these waves are actually increasing because they are basically sound waves here. If you make those um, streams vibrating, so then the same thing here. Or maybe you should think about the um, what's the speed in the waves will be the same, propagating will be the same. So the frequency here, this guy will be, because it has the longest wavelength, so it will have a lowest frequency and then second lowest frequency and the third lowest frequency. Okay. So then these are called the first harmonic that you create in the string. This is called second harmonic, and this is called the third harmonic. Okay. So the um, first, second, and third referring to the frequency from lowest to highest. Okay. All right. Um, so for standing waves on a string, then the first harmonic or the lowest frequency, the lambda is twice, okay, twice because twice of the length of L, because that's just half of the whole wavelength of the wave. So then frequency will be equal to the velocity or the speed of the stream of the wave divided by the wavelength, 2L. Okay, so You get that? Fundamental harmonic or fundamental frequency will be V over 2L, lambda will be 2L. And the next harmonics, the second one, so you will actually have the lambda, okay? So that will be equal to lambda 1 divided by the nth, okay? So the second one is the two half of the first one, okay? And then the third one will be the third of the first one, etc. Okay, so you can kind of see from the previous slide. So this guy, wavelength is 2L. This is 2L over 2, and then this guy is 2L over 3, okay, and etc. So that gives that, and then the frequency can be calculated. Okay, so frequency then will be the for the nth harmonic, it will be n times of F1, the fundamental. Okay, and then fundamental is n V over 2L. Again, you can kind of derive that. So V will be the same, but the second harmonic will be V divided by L. Okay, so then it's 2 times F1. Okay, in that case. If you guys had a toy like this when you were little, the xylophone here, so you can see the metal strips are, the lenses are varying, so that's why it's producing different harmonics, because you can see the fundamental harmonics produced is V divided by 2L. Okay, so if you have different variation in the length, then you'll have different frequency, and frequency determines what tune you are hearing. Okay, all right, so these are the equations for the wavelengths and frequencies for the nth harmonics when you have the two sides of the string fixed. Okay, so this is a figure summarize what we just learned. So for the first harmonic, okay, so there's one anti-node, there are two nodes at the end, three nodes for the second harmonic, two anti-nodes. Okay, and this the first harmonic, second harmonic, third, fourth, fifth, etc. Okay, the wavelength is 2L over m. M will be referring to the harmonics, the nth harmonics. Okay, and then frequency is V divided by 2L times m. Okay, so this is the small n there, etc. All right, let's take a look at the first example of the day here. So it says a wave traveling on a slinky that is stretched to 4.0 meters takes 2.4 seconds to travel the length of slinky and back again. All right, so let's go to another app I have here. So it tells us the slinky total strength length is 4. Okay, so we can draw this guy out here. So total length is 4 meters, and the wave travels back and forth. Okay, 2.4 seconds. It's asking the speed of the wave. Okay, so let's say if there's a wave it's traveling back and forth like this in this slinky, so going in this way and then coming back, the total time. Okay, so for the speed, we can basically use the speed equals to distance traveled divided by t. Okay, but distance traveled in this time will be 2 times the total length, because it says the wave travels back and forth, right? Divided by this time it takes. So this will give you 3.33 or about 3.3 meters per second for the speed. Okay, it's asking in part B that using the same slinky stretch to the same length, the standing wave is created, which consists of 3 antinodes and 4 nodes. Okay, so so then it's not the figure I had there. So maybe let's say let's redraw this guy. So then we will have actually we will have 4 nodes and 3 antinodes. So that means here and here we got this guy up and down. Okay, so there are 4 nodes right? For nodes is where the string vibrate the minimum, okay? And anti-nodes is where it vibrates the maximum. So anti-nodes there. So it's asking at what frequency is the slinky oscillating, okay? So in this case, we can see this is then actually a third harmonic, okay? So if we go to the slides um, and then move it backward by one slide, you'll see that this is actually a third harmonic, okay? So in this case, the wavelength should be 2/3 of the total length. Okay, so the wavelength of this guy is 2/3 of the total length L. And it's asking you for frequency. And we know that the speed of the wave should be equal to frequency times wavelength. Okay, so then frequency should be equal to the speed divided by the lambda. Okay, so it's a 3.33 actually. Let's keep one extra digit there and divide by 2/3 times 4.0 meters for the wavelength there. And this will give you, so this will give you the frequency being, take a look at my notes, 1.25. So 1.25 hertz. All right. Okay, so that's this one here. Let's go back to the lecture notes. All right. Now we just mentioned for the standing wave in the string that with balls and fixed, right? What happens if you just have one end fixed here and then the other end is open to move, okay? Or maybe in this case here, so one end is fixed, this end is open, okay? So then for the open end, it can actually vibrate to the maximum, but for the fixed end, it's going to be just a note because it's not going to be vibrate, okay? So then in this case, the first type of wave you can have is then this is the note, this is the anti-note, okay? So if you extend this guy, so this is a maximum, and then it will go down to 0, and then goes down to the negative maximum, and then comes back to 0. So you'll see that this part of the string actually then is 1/4 of the one wavelength, okay? So then L equal to 1/4 wavelength, okay, for this first possibility wave you can have. And that's this one here on the top here. For the second one you could have is, this is a node, right? And then this is an anti-node on the other end. So then you can add a node in the middle, but then it will create an anti-node there. So then this is 3/4 of the whole length, wavelength, okay? So this is then the second harmonic, but because this is a 3/4, okay? So we actually call it like 3, the third harmonic. Or in that case, n is equal to 3. Okay, so this will be the second harmonic you can create, but we actually call it third harmonic because of that. And then the next one, we will call it actually fifth harmonic because this length is equal to 5/4 of the wavelength. Okay, this is a 1/4, this is 3/4, 5/4, and then this one will be 7/4, 9/4. Okay, in that case. So wavelength would be equal to 4L divided by 1, and then 4L divided by 3, 4L divided by 5, 4L divided by 7, 4L divided by 9, etc. And frequency, so be V divided by the wavelength. Okay, so V divided by 4L times 1, and then V divided by 4L times 3 here, V over 4L times 5 here. Okay, so it's basically V over all this column for the wavelength, and you get your frequency there. Okay, so if we summarize, the for each of the harmonics, the L is equal to n quarters of wavelengths. Okay, n equal to 1, 3, 5, etc. The frequency of nth harmonics will be V divided by lambda n. Okay, and lambda 1 is equal to 4L in the case. So n times V over 4L, okay, will be your F of nth harmonics, and then that's equal to n times F1, the first harmonic, okay, so the fundamental harmonic is that guy. All right, so that's when you have one end fixed, the other end actually open. Now let's talk about the speed in the stream when you have a standing wave created, okay? So the speed of the wave you have is determined by two factors: the tension in the string, and then the second, the mass of the string. Okay, so if tension increases, the speed will increases as well. Okay, so in that case, the second factor then is the mass, total mass per unit length. Okay, so the mass divided by the length, total mass divided by the length. Okay, also determines the speed there. So if you have heavier mass per unit length, then it's heavier, so you'll result in the slow wave speed, right? So kind of makes sense. In that case, um, so let's take a look at these three quantities involved. So if we wanted to know speed of the wave, speed should be in the units of meters per second, and tension, which is a force, should be having newtons, which is equivalent to kilogram times meters per second square. So kilogram like mass times acceleration, right, equal to force. And the density, mass density per unit length should be kilogram per meter. Okay. So in that case, for the speed should be determined by the force, tension force, and mass density. So we can say velocity is equal to then F to the h power times mu to the b power. Okay. Then we can look at the dimensions of these three quantities. We can figure out A and B parameters. Okay. So meters per second for the speed should be equal to kilogram meters over second square to the eighth power times this guy is kilogram per over meter to the b's power. Okay. So on this right hand side, you can see kilogram to the A times kilogram to the B. That gives you kilogram A plus B. Okay. And then meters here to the A. The here meters is in the denominator, so it's minus to the b, meters times minus to b. So then it's meters a minus b. And second, we have just minus 2a because this is in the denominator here. Okay, so minus 2 times a. We see that there's no kilogram on this side, so that means a plus b should be 0. Okay, so we can get a few expressions here. Okay, so a plus b should be equal to 0. Okay. A minus B should be equal to 1 because meters on the left-hand side is just meters, which means 1. And then I meant 1, not 0. So let me see if I can erase that. Hold on one second. Okay. Now mess things up a little bit. Okay, so again, A plus B is 0. A minus B should be minus 1. And minus 2a should be minus 1. Okay. So then from the last one, you can see a is equal to 1/2. Okay. Once we have a equal to 1/2, then we can determine b. So from the first equation, b should be, oh, actually, let me see. A is equal to 1/2. B then should be equal to negative 1/2. Okay. Or actually, this guy, the second one should be plus. Okay, plus 1 instead of minus 1 because a minus b should be 1. Okay. So then either put a into the first equation, you can see from there, then b is equal to minus 1/2. And we kind of have to verify for the second one, right? Second equation. So a is 1/2, b is negative 1/2. So then that gives you 1. Okay, so that means, okay, we found a equal to 1/2, b equal to minus 1/2. Okay, so then this guy is 1/2, this guy is minus 1/2. Okay, so then V will be equal to just F over mu and then square root, right? Because then F is the positive 1/2, mu is negative 1/2 is from the denominator, okay? So that will give you this relationship. The speed of wave on the string is equal to square root of F over mu, okay? All right. And let's take a look on the second example of the day. So it says two steel guitar string have the same length. Okay, so both are steel, the same material, okay, and the same length. L is the same. String A has a diameter of that, and under tension of that guy. Okay, so this is for the this is F of A. Okay, tension of A. And then this is diameter D of A. Okay. And string B has diameter of that guy, so this is D of B. And under tension of that guy, F of B. Okay. And it's wanting you to find the speed ratio of the two speed VA over VB. Okay, so we're looking for VA over VB. Okay. So VA here, not UA. Okay, and we just learned that V is equal to square root of F over mu. Okay, so then this should be, if we do that, this should be square root of FA over mu of A divided by square root of FB over mu B. Okay, we are given FA and FB, so we don't have to worry about that. Let's take a look mu A and mu B. Okay, mu is mass divided by L. Okay, so the two has the same length, so L is the same. Okay, so then for mu A, it should be, or mu should be just for the mass, it should be the density, okay, of the string. So this is the volume density, okay, times the volume. Volume is equal to cross-sectional area, okay. Cross-sectional area is, if we look at the equation for that, is pi over 4 and d diameter square, okay, and times L, okay, and then divided by L, okay. So it's rho times V divided by L, okay. So you can see that L actually will cancel, okay. So L and L will cancel. So mu then is a function of the density and a diameter square, and then with the constant number, okay. So in that case, then we can see, so here, this is then equal to, actually, we'll do just FA times mu B first, because mu B is denominator in the denominator, so we'll flip, okay. And then on the bottom, we should have FB times mu of A, because mu A was the denominator in the numerator, okay. So it's kind of square root of that, okay. So for FA over FB, that's 410 over 802, okay. So no worries on there. But let's take a look on here. So this would be equal to FA over FB, okay. So we can have that taken care of first, and then times mu B will do rho of B, which is the steel, and rho of A is also the steel, so that rho should be the same for the same material, okay? And then pi over 4 is the same. So diameter of B squared divided by rho pi over 4 d of A squared, okay? So we are not given row, but they are the same, so don't worry. So we can actually cancel out that row times 4 pi, row times 4 pi. Okay. So this then becomes just FA over FB square root, and then times square root of DB square over DA square. So then that will be just DB over DA. Okay. Because you square them and square root. Okay. So FA over FB, that will give you, if you look carefully, it's like 410 over A20, right? So A20 is twice of 410. So that gives you 1 over 2. All right. Um, so then this is square root of 1 over 2 for the first one times dB over dA. So dB is 1, dA is 0.5, both in millimeters. So then that gives you just 2 of that. Okay. So at the end, you'll get at least just square root 2. Okay. Because 2 is basically square root of 2 squared. Okay. So on that, that would be the ratio. All right. So let's go back to the slide there. Next, we'll take a look on standing waves in air columns, okay, columns of airs. Okay, so if you have the same bottles at home, you can do this as a home experiment. So you can fill them up with different levels of just water, will be fine. And then below air on top, you actually probably hear different tunes. Okay, so this is then a kind of like instrument, musical instrument. If you have like organ pipes, woodwind. So then that's how it works because you are creating standing waves in the air columns. Okay, so or if you play flute or kind of similar pipe instrument, that's the standing waves in the air columns or drums. Okay, so in that case, let's take a look on the waves you created. So um, with a pipe, if you have one end closed, the other end open, so then at the closed end, the air molecules will vibrate the minimum, and at the open end, the air molecules can vibrate the maximum. Okay, so then this is what you create for your first wave or first harmonic. Okay, so this is again 1/4 of the whole wavelength. Okay, so this is the first harmonic. The second one, there's a note here, then the anti-node there. So then you add a node in the middle somewhere. There should be another anti-node there. So this is 3/4 of the whole wavelength. And then this guy, the third one will be fifth quarters of the 5/4 of the whole wavelength. Okay, so then this is basically similar to um, the scenario of the stream with standing waves when you have one end open and the other end fixed. Okay, so that's the same. So then the wavelengths, the fundamental frequency of frequency for nth harmonics, they are the same. Again, we call the first one as the first harmonic, but the second one as third harmonic, the third one as fifth harmonic, etc. Okay. All right. And then if you have the pipe with both ends open, then at the end, you will actually have anti-node and then you have a node in the middle. So this is 1/4 from center, the middle to the end is 1/4 of the wavelength, and then to the other ends is another 1/4. So 1/4 and 1/4 add up to be 1/2 of the wavelength. Okay. And that's actually similar to when you have the string, both ends are fixed, then you create like that, right? The wave like that. Okay, so they are both half wavelengths, so they are the same thing. And the second one here, again, 1/4 plus half plus 1/4. So this actually then is a full wavelength, which will be the same as the string, and then you have like that as your second harmonic. Okay. And the third one, comparing to the string, you'll have actually something like this for the third harmonic. Okay, so basically will be the same. One loop plus two half loops, that will be three. A loop is half a wavelength. So this will be 3/2 of wavelength, 3/2 of wavelength, okay? So the air columns with both ends open is the same as the string with both ends fixed, okay? And then those are the harmonics, their wavelengths and their frequencies, okay? So the same as the string with two ends fixed. If you have air columns with both ends being closed like a drum, so then this is what you create. For the first harmonic, you create this note at the end here because they are closed, then antinode in the middle here. So then this is again half of wavelength, right? Half of wavelength on that guy. And then the second one is a full wavelength, which is 2/2. And then the third one will be 3/2 of the wavelength, okay? So again, this the with two ends or closed is the same as the string of two ends closed, okay? So, and you'll be having the same equations for the wavelengths and then also for the frequencies, okay? So we are not going to just repeat that in detail. Let's take a look on the example here. So this one says an organ pipe opens at both ends. So both ends open. So that would be like this scenario. Okay. So those are the equations we will use. These are the equations. Okay. And then go back and see. And it says it has a harmonic with a frequency of 440. So this is a particular harmonic 440. The next higher harmonic is 495. It's asking find the fundamental and then the length of the pipe, and then assuming the speed of sound to be 340. Okay, so let's see here. So it does not specify which harmonic is this. This is just a particular one. So we can say or actually frequency F. We can say F sub n is equal to 440. Okay, so that's just a fourth harmonic. And the next one should be just F sub n plus 1, right? The next harmonic is the n plus 1. That should be 495 hertz. Okay. All right. And if we look at for both ends of the pipe open, then the formulas we have will be m times f1 equals to the v over 2l, okay, n times v 2l, okay, and then that's equal to the f of n, okay. All right. So basically, this will tell us, okay, so then if we do m times f1, it's equal to 440 hertz. And then if we do m plus 1, also times f1, that gives you m plus 1, that's equal to 495 hertz. Okay. So based on these two equations, we can find, because there are two equations, we have two unknowns of n and f1, we can solve for both. Okay. So you can write one in terms of the other one and then do substitution as we normally do. Or if we look at carefully at the second equation, the second equation can be rewritten as n1 times f1 plus f1, right? So it's n or n times f1 plus f1 then equals to 495 in hertz. Right, the first equation tells you that guy is 440, so n f1. So this is 440 hertz already. So then f1 will be just equal to 495 minus 440. Okay, so we can actually solve that directly. This is 495 minus 440 hertz, which is 55 hertz. Okay, so that's the fundamental. All right, so it looks like we have that taken care of. B is asking you what's the length. Okay, so if we have f1 equal to that, and then also f1 should be equal to just V over 2L. So M being 1, okay? So then L can be calculated. So L should be equal to V divided by 2 times F1, okay? V is 340 meters per second over 2 times 55 Hertz, okay? So that gives us 3.1 or 3.09 rather meters, okay? So that's the length of the pipe, the organ pipe, okay? All right. So back to the slide then. So at the end, let's talk about the beats. Okay, so beats are interference patterns in time rather than in space. Okay, so which means the two sounds or two waves are very close in frequency. Okay, so then the small difference in frequency will create a beat. Okay, so the sound also has a periodical time independence. This is a much lower frequency of independence. Okay. So if we look at the two waves, okay, so if the two are very close to each other, T1 and T2 are close to each other, so then you basically get very similar waves, but just varying in space a little bit, okay? And if you have those two add up, okay, so mathematically now cosine, this is theta 1, this is cosine theta 2, so cosine theta 1 plus theta 2 actually gives you cosine of the difference of the two divided by 2, and then cosine of the sum of the two divided by 2. Okay, so the same in that case. And the B difference will be referring to the frequencies difference. Okay, so F1 minus F2 there. So the amplitude as a function will actually oscillate with the B frequency. Okay, it's F1 minus F2. So it goes down and comes up again in that kind of sense. So the green refers to the oscillation of amplitude, okay, in that case. And then that's called the beat frequency. So it's basically the difference of the two. Okay, so when you hear that, that just means the difference of the two. So amplitude will go oscillate, going down, going up, going down, going up. Okay. Let's take a look on the example here. It says you have two streams fixed at each end are identical. Okay, so two identical streams, except, so not exactly identical, except that one is a little bit longer than the other, by 0.560 centimeter, so about half of centimeter. And it says waves on these two streams propagate with a speed of 34.2 meters per second. And the fundamental frequency of the shorter string is 212. It's asking you what beat frequency is produced if each is vibrating is with the fundamental frequency. Okay. And then B, that's the beat frequency in part increase, in part A increase or decrease if the longer string is increased in length. And then repeat A, just calculating if you get given a longer string to verify if your beat frequency actually increase or decrease. Okay. All right. So on this one here. So let's kind of sketch it out. Okay, so the first one, first string, okay, and second string, a little bit longer. Okay, so this is string number 1, this is string number 2, and this length additional is the 0.560 centimeter. Okay, on that. So the speed is given, both are that. So from F1 on the 1 is 212 Hertz. First fundamental, okay. Yeah, both sides fixed, okay. So then F1 F1 should be equal to V divided by 2L. Okay. So then we are given F1 and V, so we can figure out L. Okay. So V is also given. So this gets V. So we can find that the length of the string of the first one. Okay. So we can say 212 Hertz is equal to 34.2 meters per second divided by 2L. Okay. So this will give you your L. L should be, in this case, the 34.2 divided by 2 times 212. Okay. And this will give you 0.08066. That should be in meters. Okay. So with that, we can calculate, so let's call it FL, L1. Okay. So then L2 is a little bit longer. L2 can be calculated. Okay. L2 is L1 plus that 0.560 centimeter. Okay. So 0.08066 plus, converting that centimeter to meter, 0.00560. Okay. So then this gives us 0.08626 in meters, okay, for L2. Now, if we have L2, we can find the fundamental of the second string, right? It's similar formula as this one, but we'll call it F2, although it's the first harmonic of the second one. Okay, so F2 then equals V divided by 2L2. Okay, V is the 34.2 meters per second, 2 times 0.08626. Okay. So this will give us 198.2 Hertz. Okay. Now we have the first fundamental of the second one, so then we can calculate the beat frequency, right? Beat frequency F of beat EAT should be absolute value of F1 minus F2, and the difference of the two. Okay, F1 being bigger, so it's 212 minus 198.2, and that should be equal to 13.8 Hertz. Okay, for the beat frequency on that one. Okay. So B is asking you if this this guy increased 0.56, it's increased, then what should you get for your beat frequency? Okay, so you can kind of look at here. If this increase, then L2 increase, right? Then F2 would decrease, okay? Because L2 is in here, F2 will decrease. So then this guy will be getting smaller. So the beat frequency, the difference then should be getting bigger, right? So we can say that, so it should increase, okay? So it should increase. The beat frequency should increase. And then C, we are just verifying that, okay? So that means we are doing all over again in A, but this time we can just start with the L2. L2 now is the 0.08066 again, but plus a different number as given in the problem, and then convert it into meters from centimeter to meter, okay, 0.00761, and that will give you a particular number. I did not calculate it on my note, so that's okay. Basically, I just did that calculating F2 directly. Oh, let's call it a prime because it's a different from A now. Should be the send speed divided by now the L2, but 2 times our L2, 0.0 A066 plus 0.00761, and that gives us the new F2 with the prime. That's 193.8 Hertz. Okay. And then the new beat frequency, we can calculate it. F beat prime should be the 212 minus this new F2.8. So that gives you us 18.2, okay, Hertz. And this is indeed greater than the 13.8 that we got earlier. Okay. All right. So that's, yeah, that's the full solution for this one. Okay. All right. So quickly summarize, we learned standing waves in streams and also standing waves in air currents. And at the end, we look at the beat frequency of two sounds that are close in frequency. Okay. So that will be it for today. I will come back another time. Okay. Goodbye.